The images that I was saying was loading up as uint8 were not loading up as uint8, and that's because so Scikit image doesn't have image loading libraries of its own. We actually depend on other libraries to load images. So, for example, you have a Python imaging library, then that I believe is the default, and it'll use that to load the image, and that's what I'm using, so it loads up as uint8. If you use matplotlib, which is the second on our list of plugins, it's going to load that up as float32. So you're going to have some versioning issues. If you actually see any problems like this, please raise your hand, and Juan's going to look out for you and try and help you out. And please ask me questions if you have any while I'm talking. All right. So we're going to, as promised, we're going to move on to color spaces. So color spaces are sometimes confusing because we're just so used to RGB, but they're really, really useful for certain applications. So Scikit image actually provides functions for converting between color spaces in its color module. So again, we're kind of partitioning out our functions into different modules for easier reuse. So there's a color module with RGB2 functions. So if you tab, maybe unfull screen. Tab is not working anymore. Okay, if you do that on your, Yeah. Yeah. I mean, oh, yeah. Oh, yeah. Okay, sorry. But it was already, okay, don't worry about it. So if you do color.rgb2 and then tab, then you can see we can convert to grayscale. We can convert to HSV, hue, saturation, value. And the color space that we're going to be using is called lab, or LAB. This is luminance. The first channel is luminance, or lightness. And AB, which is just some 2D space for colors. Okay, so if we convert our image to lab, we get back a lab image. You print out the shape, and it looks exactly like the shape of the image that I had before. It's 300 pixels high, 451 pixels wide, and has 3 color channels. So let's just try and plot this on matplotlib, using matplotlib. And if we do that, we get this noise, because matplotlib and most image processing libraries or plotting utilities are going to plot this, are going to expect RGB, right? So how might I plot this so that I can see something useful? Exactly. So we know how to slice out a channel. We just take all the rows, all the columns, and then let's say the very first channel. So that's my slice. If I run that now, I get a picture of a cat. Okay. So we have another exercise for you. Basically use the lab color space to isolate the eyes on the cat image. So you're going to want to play around with those lab channels, plot them, see what they look like. You might want to take a look at the Wikipedia page on lab color space, but it's really not necessary. You should be able to figure this out just by looking at the LAB components of the image. I'm sorry? Oh, yes. So you just slice out the last channel, or the first index of the last channel. Oh, I am actually using square brackets to index here. Yeah. Oh, yeah. Right, so I've hidden my brackets. right, so I'm just going to give a hint. Those of you who are have already plotted all the channels, go ahead and continue. So a really quick way to plot all the channels is to just use the IMShow function and plot all the channels. So we already learned how to iterate over the channels of an image. So we can use roll axis to move the color axis to the front. So the last axis, -1 to the front. And then pass that along to our IMShow function. And I'm missing a brace. And we have our L, our luminance, our A channel, and our B channel. So axis -1 just moves the last axis to the front. And the star, so I expected any number of arguments, each of which was an image. So I'm unpacking this tuple using this star. Has anyone been able to threshold the eyes out? Yeah? Nice. So I'm going to actually rewrite what I just wrote a little bit, just so it's a little easier. So I'm unpacking these into the lightness. I think it's lightness. It might be luminance. Do you know? Oh, luminance. OK, whatever. So I'm unpacking this roll axis into the luminance A and B. So this roll axis just moves those color channels to the front, and that's the default iteration. So this tuple unpacking is just going to take those 3 channels, and I'm plotting luminance A and B. Right. OK. So we can see from this series of images that the eyes show up pretty well in all of them. But you notice in the middle image, the A channel, that it's distinctly darker than everything else, right? So this is what you want to threshold. So what should I pick my threshold as? 2. How did you get 2? Experimentally. OK. You did what? Otsu? OK. That's not bad. That's a good first shot. But I encourage you, whenever you're just picking intensity values, to use plot a histogram. So we can use IMShow with histogram on our image. So ignore the actual image, because LAB color spaces are going to be plotted correctly. But the histograms are still going to be useful. So if you look at, so let me just clarify, this expects RGB. So the histogram is plotting L, luminance, as red, A as green, and then B as blue, right? Are you going to go with just A or not? Yeah, with just, yeah. Oh, with just A. Oh, yeah, that's a good idea. Right. So if we just wanted to plot our A channel, you see our dark eyes. And you look at the histogram and you can see that it tails off close to 0 or 2 or 5 or whatever. So I'm just going to combine this image, or sorry, this value. So I'm going to take, oops. So I'm going to plot the image thresholded with, oh sorry, not the image, just the A channel with values greater than or less than, let's say, 2. And you can see that it picks out the eyes really well. Right. So all the values from this image that were less than about 2 extract the eyes really well, because it's much, the eyes are obviously much darker than everything else. Okay. In the interest of time, I'm not going to do the nose, but you can see that in the A image, the nose is also brighter than the things that are surrounding it. So you can threshold there as well. Okay. All right, so that's actually the last section, or the last part of this section. Are there any questions before we move on to the next section? Yeah. Mm-hmm. Right. So that just has to do with the particular color space. So like I wrote here, the first channel is the luminance, which is pretty easy to understand. It's just the pixel intensity. If you go to this Wikipedia page, it explains it a little more. It's just a 2D color space. It's not easy to just give a label to it. It's just a 2D space. So it looks kind of like these over here. Okay, so we're going to move to the next section, which is image filters. So just go back to your index, click image filters, or if you're looking at the notebook directory, it's one_image_filters. All right, so with image filtering, I'm going to start really basic, just to make sure that everyone is on board. So I'm going to talk a little bit about some image filtering theory with some local filtering. So I'm going to start off with a 1D signal, a step signal. So all it is zeros on the left, tens on the right, and a sharp jump in between, a simple step function. I'm also going to add a little bit of artificial noise, really, really artificial noise, just adding 1 to every other value. And I give this, get this little sawtooth. So that's a noisy signal, let's say. So the simplest way to make this curve look similar to the original curve is to just average adjacent values. So just take pairs of elements and add them together, divide by 2, right? And so we can do that with NumPy slicing. So this takes 0 to n-1 from the signal and adds it with 1 to n. So these are adjacent slices, essentially, and then divides by 2. So that's just a simple average. Add pixels next to each other together, divide by 2. And we get a signal that's smoothed out. It doesn't match the original values, but we're going to ignore that. We can also, so this was done using NumPy slicing, and those of you who are really familiar with NumPy slicing should be able to see what this does. Another way to express this is just using convolution. So I can define a convolution kernel. So this is my convolution kernel, which is just a small array that I'm going to move on top of my original signal. And I'm going to multiply all the values using the values in this convolution kernel. So I just have 2 elements with 1/2 and 1/2. So I multiply pairs of pixels, or I guess pairs of elements in this case, by 1/2, add them together, and that's the result of the convolution filter. And I get the exact same thing I got before. Is everyone clear on that concept? Okay, cool. So let's move on to images. So we're going to apply the exact same technique to images. And I'm going to use a really, really simple image to start off. So this is a whole bunch of zeros with some 1s in the middle. And if you plot this, it just looks like a black square with a little white square in the middle. Okay. So we're going to do the exact same filter. So the mean filter that I just showed you, we're going to do the mean filter for an image this time. The mean kernel that I'm going to use is shown here. I'm This is a 3 by 3 array, so it has 9 elements. So I want to divide by 9. So I want to divide every element under that array by 9 in order to get the mean. Right? So I have 9 elements, divide by 9. And what I'm going to do is I'm going to take this kernel and move it all over my image, multiplying the values under the kernel by those values, and add them together, and that's my result. So to actually visualize this, there's a little demo here. So if you have IPython 2.0, which you should, then you should be able to run this little interactive demo. So what I've represented here is in the yellow region, that's my kernel. That's the size of my kernel. There's a little bit of yellow that's running outside of the image right now. And the red spot here is also part of my kernel, but it's special because that's the value I'm going to replace in my original image. So at first, it's very boring. So the kernel, like I said, is going to move across the image. So it's going to just scan the rows. It's very boring. I'm multiplying all the zeros in my image by some number and then adding them together. So adding a whole bunch of zeros together. Nothing happens in my image. And then after it finishes that top row, it goes to the next row. And that's when things start, interesting things start happening. We get our kernel to lie over a white pixel. You probably can't see it on my screen, but it replaced the red pixel here with a slightly brighter pixel because this kernel was over this, this white region. If we move another step, you can probably see this now. I have 2 pixels under my kernel, so I have a slightly higher value that I'm replacing this red pixel with. Right? So I hope that's clear with everyone what that convolution is doing. OK, so we just stepped through, and the result of the mean kernel is some image that looks a little smoother than my original image. So here you can see that when my kernel was over all 1s, it just replaces it with a 1. So nothing changed by this pixel because the mean of a uniform number of values, or uniform values, is probably not on. Is this OK? Cool. All right, so play around with that on your own time. I think I'm going to move on from this little widget demo. OK, so let's look at those values, the values that you get from the mean filtered results. Notice that whenever the kernel was over 1 pixel, you got 1/9 back, because that's what we expect. When it was over 2 pixels, it's 2/9, et cetera, et cetera. OK, so now we're going to apply downsampling to an actual image. But since we're looking at a very small kernel, this 3 by 3 kernel, we're just looking at nearest neighbors. Then we want to use a downsampled image. So I'm going to use NumPy slicing in order to get a downsampled image. So I'm taking every 10th row and every 10th column of the image. So that gives me an image that looks really grainy now. OK, so we're going to apply the mean filter to this real image. So you see that the result has less noise. This grass earlier looked like maybe it had some features in it, artificially had some features in it. But after smoothing, you remove that noise. You also smooth the edges. So borders between black and white regions are now kind of rounded in intensity. So that's what a mean filter is. It's a smoothing filter. So that mean filter was just an example of how to build a filter and how filters work. When you're actually doing image processing, you don't want to build your little convolution kernels every time. So there's a lot of filters that are predefined in Scikit image and in SciPy ND image, for example, that you'll be using on your images. So I just want to talk about a few of the essential ones, the most common ones. So the most common smoothing filter is the Gaussian filter. So it's similar to the mean filter. It has some number of values in an array, but instead of having all the values equal and weighting a far away neighbor the same as a close by neighbor, a Gaussian filter weights nearby neighbors more than far away neighbors. If we actually look at the results of a Gaussian filtered image, it doesn't look that different than a mean filtered image. So nothing too special there. If we look at a larger image with a little more detail and use a larger kernel, then you can actually see some differences. So you see the Gaussian image looks really, really smooth. It's great. But the mean filter image has these sort of artifacts. And that's because you're weighting a far neighbor just as much as you're weighting a nearby neighbor. So I might be up in this white region, and I might grab some pixels in this black coat, and I'm saying that these have equal weight as the nearby neighbors, which is completely false. So you're going to get a much better result, much less noisy result with a Gaussian filter. All right. The next filter that we're going to be talking about is basic edge filtering. For this example, we're going to actually go back to our 1D case just to make sure that everyone's on the same page. So I'm going to look at a step signal. So we have zeros on the left, ones on the right, and this sharp jump in between. And this is what we're going to call an edge. So an edge is just the boundary between one uniform area and another uniform area. And that's what we're looking for here. That's what we want to identify. So the simplest way to identify this in a signal is just to take neighboring differences. So if I say 0 minus 0, so just take difference of nearest neighbors, then I get 0 back. If I take 1 minus 1, then I get 0 back. But if I'm on the edge, I get something different. So to express that using a convolution kernel, we're just going to say multiply one element by 1, and then the neighboring element by minus 1, and add them together. So subtract neighbors. And if we convolve our image with this difference kernel, then we see that the zeros had zeros response, the ones had 0 response, but the gap right in between, the transition in between, you're subtracting 1 from 0, and you get a jump. Right? Is that clear? All right, so now we extend this to 2D. So difference filters in 2D. So I'm not going to use a convolution kernel here, just because you're going to be writing a convolution kernel in an exercise in just a few moments. So I'm just using NumPy slicing. So here I take the vertical gradient by slicing rows. So I subtract row 1 from row 0, row 2 from row 1, et cetera, and that gives me my vertical gradient. I do the same thing with columns, and I get my horizontal gradient. Now, if I plot this, I get something that doesn't really look like what I expect. I want the edges, and I have just a whole bunch of white noise. Any guesses? Exactly. So I warned you earlier that doing math with unsigned integers is a terrible idea. If you're subtracting 1 from 0, then subtracting 1 from 0, then you can't represent minus 1. You have an unsigned integer, so it does the stupidest thing possible, and it doesn't throw an error, it doesn't raise a warning, it just wraps around the 255. Oops, I meant to actually print out I thought I had a. So I meant to print out that this pixelated image was actually a uint8 value. So to fix this, sorry, let me get my line. To fix this, we're just going to convert to float. So import skimage. Oh, yeah, that's right. Thank you. So I'm going to say my pixelated image is equal to skimage images float. Those of you who are using systems where the image was imported as float already don't have to worry about this. So the result is a lot more like we would expect. We have some dark regions. So this is the vertical gradient. So a vertical gradient is going to identify horizontal edges, and a horizontal gradient is going to identify vertical edges, right? Because the difference of two columns is the horizontal gradient, but it's a vertical edge. So is what you're seeing in this image somewhat clear? Oh, sorry. Oh, okay. The images, oh, sorry. Oh, let me. Right, so I just converted that image to float so that when I subtract a high number from a low number, I don't get, or I actually get negative numbers as opposed to wrapping out around to another positive number. So is the image somewhat clear? So we have bright and dark areas for both, for edges. So one direction of the gradient, so if I go from, I guess in this case, white to black, it shows up as dark. But if I go from black to white, it shows up as a light gradient. But both of these, the magnitude of this defines an edge. Okay. So just returning to our kind of very, very simple example of the bright square, if we take vertical gradients of this, then you can see what the result looks like. In one direction, we get a black result. In another direction, we get a white result. But the magnitude is the actual edge that we're concerned with. But you'll also notice from this image that this differencing wasn't that great. It returns the edge in between pixels. But usually when you're doing a lot of image processing, you want the result to align with your image pixels. So you don't want to just do a simple differencing operation. And that's where convolution comes in. So here you can just see that we've actually changed the shape of our image. All right, so you're going to pretty much do a very similar thing to what we just showed. You're going to make an edge filter for the image. And you're going to find both the horizontal and vertical edges of the image. But instead of using differences, you're going to create convolution kernels. Oh, and I think I have some sample code, right? Yes. All right. So I've just filled this in with some dummy kernels. You're going to erase this NP1s entirely. This is a do-nothing kernel. It just multiplies every pixel by 1 and returns the pixel itself. But I just wanted it to compile, so I filled it in with something reasonable. All right, so I'm going to keep working. I just want to, for those of you who aren't far along, I just want to show how to represent the original array, or sorry, the original difference filtering that we did up here. So just looking at neighbors, what that convolution kernel looks like. So if we want a horizontal edge, then we want to multiply, or sorry, horizontal edge kernel, then we want to multiply or use a kernel that has a vertical layout. So we want a column vector of 1s and -1. So just to represent what we saw earlier, we took the difference of nearby neighbors. So a column array is going to look like this. So this is a 2D array. Oh, sorry, let me undo the green there. So we have a 2D array. Each row has one value. That's actually a do-nothing filter. So I'm going to add a -1 here. And if we run that, we get a difference over here on the right. Similarly, with the vertical edge kernel, we want a 2D array, but this time we want a row array. And that looks like this. So this is just the brackets can be a little confusing. They're just kind of creating the row and column vectors that I need, or column arrays that I need. Oops. Oh, sorry, array. So that's the first step. I ask in the example to actually give a centered difference as opposed to this skewed difference that we have here. So how do I make sure that we're not biasing the edge in one direction? Add another element. So what should I add? Another 1. So if I do something like this, what do you mean by adding another 1? Right, exactly. So I'm going to say multiply myself by nothing, multiply this neighbor by 1, multiply this neighbor by -1. So now the edge is going to be right here in the middle, right? So this is a way to prevent skewing of your results. So this doesn't look that different. It's a little wider, but it doesn't look like it's centered. I should have had an example with the little black square and the white square, but I'm going to just move on in the interest of time. OK, so you don't have to create an edge filter either. This is just an exercise. The classic edge filter is called the Sobel filter. And it actually looks a lot like the filters that you have generated. If you look in the documentation, you can see, oops, oh no, I completely lost it. OK, let me just open that. Oh, did I? Yeah. OK, yeah, OK. Wait, where are the? Oh, this is the Sobel, though, not the V Sobel. OK, let's abandon that. Oh, actually no. Let's just click on this. I'm sorry. Oh, it's big now. OK, so you can see that this. OK, let me unfull screen and do it this way. OK, so so earlier I did 1, 0, -1. This does a little. It uses a 2 here, and it has other values on the diagonals as well. So this is basically just to get a little more even distribution. So if an edge is slightly off horizontal, or no, I guess vertical in this case, then it does a much better job of resolving those edges. Right? So it just adds a couple of diagonal elements to that array. But it's basically the same as what we just showed you a second ago. OK. And so if we actually run the Sobel filter, so this was what I just showed you was the vertical Sobel filter. There's also a horizontal Sobel filter, and those look for the horizontal and vertical edges. But the Sobel filter just combines the two and takes the gradient magnitude. That's usually what you want. You don't care about the orientation of an edge, usually. And if you look at the actual image, then you get a result that looks like this. So you can see it picks out the edges pretty well. So one caveat about using difference filters, if you've ever done numerical methods, you know that derivatives are noisy. So usually it increases noise, whereas integrals smooth images. If you're doing difference filters or looking for edges, then it's a good idea to smooth the result first because noise can cause lots of problems otherwise. All right, so I had an exercise scheduled, but I think I'm going to actually skip that and move on to the next section. Like I said, we'll have solutions after this course is over, so you can always take a look at it then. So I'm going to move to notebook 2. So if you go to the index, it's called feature detection. And it's, if you're just looking at the notebook directory, it's 2_feature_detection. All right, so hopefully everyone has that pulled up. So I just finished talking about edge filters, but I'm going to talk about edge detection now. So what's the difference? So edge detection, we just did it. We did run our Sobel filter, and we get this edge filtered image. But sometimes so this edge filtered image tells you the likelihood whether or not a pixel is on an edge. It doesn't tell you whether something is or is not on an edge. So sometimes you want something saying, this is an edge, this is not an edge. And so that's the whole point of edge detection. So we've already learned about thresholding. You know that you can say, oh, if my gradient magnitude is really high, then it has a high likelihood of being an edge, right? But if we do that, we don't really get great results. So this is, I played around with some values, and this is the best result that I could get with just simple thresholding. So there's a couple of really bad things about, I'll use the mouse so that everyone can see. There's a couple of really bad things about this result. You get this large blob here, for example, where the camera is. And we know that edges should be thin. I mean, that's kind of how, that's one of the elements of its definition. It's going to be thin, whereas this is just a huge blob. So it definitely shouldn't be an edge. Another thing is that we have some gaps where edges kind of appear and disappear, right? So for example, on this man's coat, there's this really strong edge, and then up here near the elbow, and then down near the legs, there's a strong edge. But there's just this gap in between because the threshold wasn't high enough. But ideally, we know that if we have one edge here and one edge here, then this gap in between has a very high likelihood of being part of that edge. So we want to use that knowledge, whereas thresholding just says, hey, everything greater than this value. Right? So that's what the Canny edge detector does. It tries to use our knowledge of edges in order to better detect them. So the steps are as follows. A Gaussian filter, which we've seen earlier, a Sobel filter, which we saw earlier, and then two new elements, 2 new steps, which I'll talk about in the next few slides. Okay, so the first step is Gaussian filter. Like I said, if you're doing difference filters, you want to smooth your image first. Otherwise, noise is just going to blow up. So we just apply that to smooth our image. Next, we run our Sobel filter. So that, we've kind of ran through that for a very long time, so, or edge filtering in general. So that should be clear. It just gives us the edge all around our object. And the next step is new. It's called non-maximal suppression. And the goal of this is to suppress gradients close to stronger gradients. So it's basically saying, look for a better edge. If there's a better edge nearby, then use that. So here's an example that I put together. It doesn't actually use a function for non-maximal suppression because that's kind of embedded in our Canny function right now. But the basic idea is we take these very sort of thick edges, these blurred edges, and we try and find the best edge possible by suppressing maxima, or by suppressing values that are lower than the current pixel. So for example, if I had 2 pixels here, I want to suppress values that are normal to the edge. So if I had 2 pixels that were about the same on this edge, I don't want to suppress a neighboring edge pixel. I only want to suppress values that are normal to that edge. So I look for my edge direction first, which is this diagonal I'm drawing with my mouse. And I want to suppress values that are in the direction normal to it. If If I'm larger than these pixels that are across the normal direction, then just wipe those away and ignore those. That's a little hand-wavy explanation for how that works. I'm sorry. But the result is that we get a thin edge, which is really important. So we don't keep all these other pixels that are nearby. All right, so the next major step is called hysteresis thresholding. And the goal here is to prefer pixels that are connected to edges. So this is applying what I explained earlier. If I have an edge here and I have an edge here, then the point that's right in the middle is more likely to be an edge. And we're just applying that knowledge here. So hysteresis thresholding has two thresholds, a low threshold and a high threshold. And the low threshold says, hey, this gradient might be an edge. And the high threshold says, this pixel is definitely an edge because it has such a high gradient, right? So you use these two thresholds to find the edges of the image. So I'm applying this demo to just the normal gradient magnitude. So this is before non-maximal suppression because we don't have access to that image. But it gives you an idea of what we're doing. So I've plotted the high threshold in red and the low threshold in yellow. And what this basically does is it uses those red pixels, those definite edge pixels, as seeds, and then you spread out along the red and yellow pixels until you reach black pixels, or non-labeled pixels. So everything, all these yellow pixels, I guess look at my mouse if you can see it. All these yellow pixels that are connected to the red pixels, they're going to become an edge. But the yellow pixels that are islands, that don't have any connection to any red pixels, any of the seeds, they're just going to disappear. Right? So that's the basic idea of just hysteresis thresholding. You have two thresholds, a definite edge and a possible edge. So all four of those steps are wrapped up in what's called the Canny function in Scikit image. So if you, we're going to go to this demo. This is actually kind of a mini exercise, actually. So here's, nope, that's not our demo. So here's our demo. We're going to play around with the Canny filter from Scikit image. So it's in the filters module of Scikit image. And it takes an image as its first argument. And it takes a number of keyword args. So those of you who may not be that familiar with IPython's interact function, any keyword arguments passed to interact, so for example, a equals 1, that's going to get passed to the function that's defined here, so the Canny demo function. So a equals 1 is going to get passed to Canny demo. These star kw args is going to take any keyword args and just pass it along to this Canny function here. So the goal here is to figure out what parameters to pass to the Canny function, and also what range of parameters to pass along. So if I pass a equals 1, it's going to give me a slider of integers, I guess centered on 1. So if you actually read through or look at the past 4 steps, there should be 3 free parameters that you can adjust in the Canny filter. I don't think it mattered in my system, but that if you're getting a lot of noise, then maybe.
Yeah, you might want to just do it and just It's also good to figure out, because picking a threshold, so you want to figure out what the range of your, actually, is it the same threshold? It's not the same threshold.
I'm not sure, actually. Is anyone having problems with how to pass arguments from interact to Canny demo? All right, so just really quickly, the three parameters that we had were sigma, which is the standard deviation of the Gaussian filter that we used at the very first step, so the smoothing operation. So this controls how smooth the input image will become. Sigma, the standard deviation, is just going to be in units of pixels. So how many pixel neighbors am I going to go out, or roughly how many pixel neighbors I'm going to go out. So here I just pick a sigma between 1 and 10. I can move this slider back and forth. So if I smooth my image a lot, then my edges just disappear, right? But if I use a very low smoothing, it's really noisy. All the details in the coins are kind of picked up. The low threshold and high threshold are the other two free parameters. So I'm going to use some values, sorry. Zero to 0.5. I don't remember what a, yeah. I forget if it's float or integer. Oh, that's noise. So I think it's going to be in integers, actually. Oh, that's a good point. OK, so here I'm using threshold values 1 to 100 for both the low and the high. Obviously, this is just for creating the sliders. Obviously, high threshold should be higher than low. Just play around with that or whatever values you have. I want you to get a sense of what the low and high threshold does. And I want to ask you a question after that, too. So the goal is just to get a feel for the parameters, not to try and get the best edges possible right now. Yeah, you probably want the edges of the coin. All right, so I'm playing around with the high threshold now. Can anyone tell me what the distinction is between the high and low threshold as far as the practical output? Like, how it changes things? Yeah, yeah. But practically speaking, any other insights? Right, exactly. So the high threshold tends to say whether or not something is even on an edge, right? So large pieces of this will disappear, whereas the low threshold kind of tells you how long these edges will go. So you get some parts that kind of disappear, but edges tend to taper in intensity as you go out towards dim areas. So that low threshold is going to just kind of shorten your edges, whereas a high threshold is going to say whether or not this island is even an edge at all. Okay, so we're at 3 right now. Let's take a 5-minute break, and then we'll continue to the next section.